Hello, students, and welcome to the last episode of Physics with FOM for your chemistry class. Today's date is April 17th, and this is day 15 of your video AMI. Today, I just wanted to go over two things. One, the practice problem that I gave you, the difficult one, and then what EM radiation is, which is pretty important. So let's go ahead and start doing this. So I have a problem. The problem that I gave you, you have a wave with a unknown frequency. So in my equation, I have speed is equal to the wavelength times the frequency. Well, I don't know that. I'm going to try and figure it out, though. I do know the speed. I tell you that the speed is 2.45 times 10 to the 8th power. That's wrong. That should be the 8th. Let me fix that. There we go. And it's got a wavelength of this. So I know the speed, I know V underline, and then now I'm going to try and figure out what that frequency is, but I know this. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I don't know the frequency. Well, that right there is actually 650 nanometers, which is roughly in the yellow range of colors, getting really close to green. Actually, could be like green, yellowish green color. That's visible light. So I know this wavelength, and I know this speed, but I don't know frequency, which is on this side. So we're going to use algebra. We're going to divide this by itself. 4, 5, 6, 7, 8, 9, and that cancels that out because when you divide by yourself, it cancels out. But whatever I do to this side, I have to do to the other side. So I'm going to divide by 0.000000650, and I'm going to come out with a really large number. I'm going to bring up my calculator. Oh my gosh, it saved the problems from the previous day. How did that happen? So I'm going to clear this out. I'm going to take 2.45 is actually 245 million. You should have taken that number as scientific notation to help you out, but it's 245 million. So 245, 1, 2, 3, 4, 5, 6, and we're going to divide that by that really, really small number, which is 0.123456650. We're going to come out with that monstrosity of a number. Now, I'm not requiring you to round this to any specific type, place, but to make your life easier, just round it to 3 sig figs. I'll tell you on the assignment, round it to 3 sig figs. That comes out to be 300 and, let's get that out of the way. So you can see 376, well, that's hundreds, thousands, millions, billions, trillions. 376, 1, 2, 3, actually I would round to 377, 0, 0, 0, 0, 0, 0, 0, 0, 0. Wow, that's a big number. 1, 2, 3, 4. 2, 3, 4. Yep, that's it. And then what's our unit? Well, we're calculating a frequency, so that would be hertz. There you go. That is a extremely large frequency. If you want to put that into scientific notation to help you out, or maybe you want to know like what unit that would be, like what prefix would you use? Well, if you start over here, this would take you to kilo, mega, giga, and then after that is tera. That would be 377 terahertz, which is a really high frequency. But if you want to just put that into scientific notation, it's up to you. 3.77 times 10 to the 3, 6, 9, 12, 13, 14. The 14th power. And then our unit is hertz. There you go. That was your difficult chemistry question. But we're done with that. The last thing I want to cover is light. It comes in all different types. Here, let me lower my screen there. And then I got to make sure I'm actually recording. Here we go, and you can see me. There we go. Light. There's different types of light. light fits into a category called electromagnetic radiation. It's any type of wave that is capable of transmitting energy while moving through a vacuum. And when I say a vacuum, I mean the vacuum of space, where there's nothing there to impede or get in the way of the wave's movement. Now, electromagnetic radiation includes all types of energy waves, includes radio, microwave, infrared, visible, ultraviolet, or UV, X-ray, and gamma rays. And you've heard of these in some context. And what's cool about electromagnetic radiation is that it actually creates a field around it called an electromagnetic field, which is the picture that you're looking at. Now, what an electromagnetic field is, it's a field that's produced by a moving electrical charge. That moving electrical charge is the light wave itself, and it creates an electromagnetic field. It has an electric component, and then it has a magnetic component, and that's what that picture is demonstrating. So the red is the electric field. It's the charged field. But right next to it, as part of the wave, is the magnetic portion. See, when light travels, it creates a magnetic field around it. In fact, when any kind of electrical charge travels, it creates an electric or a magnetic field around it. And that's what you're seeing, the magnetic field. If you've ever heard of electromagnets, which I believe I've showed the class before, you take essentially a whole bunch of wire and you wrap it around something like an iron core, and then you attach a battery to that wire. You complete a circuit. Well, that electrical current, as it moves through the wire, it creates a magnetic field around it. And so electromagnets are extremely powerful because you have all of this charge going through all of this metal wire, and it creates this really, really strong magnetic field. And that's what you're seeing, the electrical current moving, and it creates the magnetic field around it. And it always goes, and it's pretty much always perpendicular, kind of moves like this, where this is the electrical field, that is the direction, and that's the magnetic field of that wave. So it's pretty cool. We're not going to go into any more detail, but any kind of electricity creates a magnetic field around it, and any kind of energy wave creates a magnetic field around it. So the EM radiation is actually part of a spectrum. It is a range of waves with different wavelengths, and here's what the EM spectrum is like. I wouldn't expect you to memorize any of this, but hey, if you ever see this picture, you kind of know what it means. These are all the different types of EM radiation. They fit on a spectrum. A spectrum is a range. And here at one end of the range, you have radio waves, which have the longest wavelengths, all the way to gamma rays, which have extremely, extremely small wavelengths. Wavelengths that are essentially the size of atomic nuclei. Those are really, really small. If you have a longer wavelength, once again, you have a lower frequency because you have fewer waves traveling per second. For radio waves, you're going to have wavelengths of around, 100 kilometers, which is a huge difference, huge distance, to 1 millimeter, which is very, very tiny. I can barely hold my fingers to make a wavelength of 1 millimeter. But then you go all the way down to something like visible light, the light that you can see. Remember Roy G. Biv, the color of the rainbow? Well, they have their own specific wavelengths. So for example, red here has a wavelength of around 740 nanometers. But then as you go closer to violet, that wavelength gets smaller and smaller until eventually you have wavelengths of around 380 nanometers, which is really, really small. And that would be in the violet end of the spectrum. Then after that, you can't see that light anymore. This is the only light we can see, visible light, right there. And then you go into ultraviolet, which, used for tanning, X-rays, and then gamma rays, which are the most powerful rays out there. So what do we do with all of this? What is EM radiation for? Well, we use every bit of it. Humans, in our ingenuity, have found ways to use all portions of the EM spectrum to our benefit. For example, radio waves are used for communication. Things like your radio stations, you pick up with through through radio waves. Your internet, your wireless internet, your cell signals all go through radio waves. Then you get to microwaves, which you can use to cook food. We use them in mobile phones, like our phones actually produce microwaves. We also use it for radar and speed cameras to see how fast people are going. Jerks. You also have infrared. Infrared can be used for cooking. We can also use it for communication. We have little bitty remote controls that send out a little bitty infrared signal that's picked up by some kind of receiver, and it tells the device to do something. We also use it to do imaging. If you've ever used or seen infrared imaging, like what the Predator uses, there you go. It picks up heat. Yeah, I don't know what's going on there. You're gonna have to figure that out. We use visible light. Duh, you can currently see me right now because of visible light. We'll cover up that disturbing picture. But we also have ultraviolet radiation, which we can use for tanning. We use ultraviolet radiation for insect lamps. You know, those buzzing lamps out there, and then the flies or whatever insects get really close to it, and then it zaps them. Well, that's because those insects can see in the ultraviolet range. We can't see ultraviolet radiation, but they can, and it attracts them, so they naturally fly to it. But there's a lot of current going through it. When the insect touches it, zaps them to death, and it produces that very, very pleasing sound of insects being burnt to a crisp. We also use UV radiation to sterilize, like surgical tools. We use it to sterilize any type of equipment. When I say sterilize, I mean we use it to kill any bacteria. We use it to neutralize any viruses or any other types of organisms that might contaminate that machinery or tools. Obviously, we use x-rays for seeing bone damage. We can see mechanical issues. We can also use x-rays to see through objects. For example, the airport scanners, they use x-ray imaging to see what's in some type of backpack or suitcase to make sure there's nothing bad in there. But then we also use gamma rays, which if you sat through the nuclear medicine career day presentation I had, we had the couple that came in and told us everything about how they use gamma radiation. Big thing is we use it to kill cancer. Chemotherapy essentially uses radioactive chemicals that release energy that kill cancer cells. And we do that through the use of radioisotopes, unstable versions of elements. We can use it as tracers to go through the body, and they go to specific portions of their body, and then we use some type of imaging machine to find out where those chemicals are and see if there's any problems with it. And then finally, we can use gamma rays for the sterilization of medical equipment. These are all things that humans do to use portions of the EM spectrum. Well, that's going to be it for today. You will have an assignment on the Google Doc, and then once you're done with this assignment, all assignments should be done for the past 2 weeks. You can go ahead and turn that Google Doc in, and you will get a grade for that. So until next time, I hope everything's going well. I hope that you get as much help as you can from the internet or from me, or maybe even ask a friend. But this was the longest video this week. Sorry, it's a lot of stuff. All right, I care about you guys. Let me know if you need anything. I'll talk to you later.